Okay. Is my screen visible?
Yeah.
Yeah. Okay. Okay. So I'll start here. So I'll cover certain basics okay only, and then we can follow those steps for the programming assignment. So the encoder block, how does it look like? So I'll give you an example that, for example, we have got a sentences like that. I am going to Delhi uh, tomorrow. Okay. Second is Delhi is my home. Okay. I am going to my home. Okay, just it is a simple example. One, two, three. So what do we do? Like in the GA, also they have asked that what should be the token size and all that. So if we the see the sequence first, we build the vocabulary. So just it is a simple example. So vocab will be I am going to Delhi tomorrow. Delhi is there. Delhi is my home. I am is there. Going is there. To is there. My is there. Home is there. So this is the vocabulary, and vocab size is 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. And which is the maximum sequence? 1, 2, 3, 4, 5, 6. So this is my maximum sequence length. This becomes my token. So what happens when I feed it to the encoder? I will feed it only six at a time. One, two, three, 4, 5, 6. So first I will feed I am going to Delhi, going 1, 2, 3, 4, 5. I'm going to Delhi tomorrow. So this is 6. Second, when I will feed Delhi is my home. So this will become Delhi is my home. And here I got two choices. Either I can do padding here or I can do padding in the starting. So if I do padding here, it will become blank 0, 0. The third key when I'll feed I am going to my home. So again it is 6. So how do we build the token IDs basically? So vocabulary is this. I am going. So I give some numbers to that. For example, I start like 0, 1, 2, 3, 4, 5, 6, 7, and 8. So I take the example of first only. So this becomes 0, 1, 2, 3, 4, going to 5. Okay, here it will become 4. Delhi is 6. My is 7. Home is 8. And then 0, 0. Then again here 0, 1, 2, 3. My is 7 and home is 8. So these are my inputs: 0, 1, 2, 3, 4, and 5. Now all these words they have got embeddings. So that is known as embedding size. So I, for example, in the programming assignment, they have given the embedding size okay, 32. So this 0 which is there, this word has got a vector of size 32. It has got some value 0.01, 0.2, something embeddings like we have learnt in our earlier course. Is this clear till now? Everybody? Can somebody give me a yes?
Yeah.
Yeah,
One question.
for the
Yeah.
for this embedding, we are using a torch function, right?
Yes,
Embedding
yes.
function.
So we are
And
using nn dot embedding,
yes,
and we are giving the size of that. Okay, that what is the size?
and this six is depends on the sequence length, right? It can be anything.
Yes, yes.
Yeah.
So they have got the embeddings, and we are giving the token. The token they have got, and they are giving me the embedding.
And one more question. So we are using only embedding here, right? We are
Yes.
not using positional encoding. So encoding. So I'm
Yeah.
learning
In
about that.
So in the first part, what happens? We are
Mhm.
not using the positional encoding.
Okay.
However, you are right. Yeah, what do we have to do? When we have got the length of a token,
Hmm.
irrespective of the word, whatever is there, we
Hmm.
find the positional encoding.
Yes.
Okay, that is
Yeah,
the
yeah.
that is in the last part of the programming assignment, and we use the sign and like a cos as per the original paper, and when
Hmm.
then we add this positional encoding to the embedding.
Hmm.
So what happens when we get the output? We also get the semantic relationship between the positions also.
It will be a point-wise addition, right?
It is a point-wise addition. You're right.
Okay. Okay,
Okay.
thank you.
Yeah.
Yeah.
Okay. So now I will just so in this there are two ways of taking that either. So I was taking this example that I am going to Delhi tomorrow. Okay. And if I take the row vectors, then this becomes 32 size, 32 size, 32 size, 32 size, 32 size, and 32 size. So this becomes 6 into 32. And when I pass, so for example, this was one sentence. If I pass 10 sentences in one go, then this becomes the batch size. And then my input becomes 10 into 6 into 32. Is that okay?
Yes. Yes.
Yeah. Just give me a second. Okay. So this embedding which takes place, it takes place before the encoder layer.
Sorry, could you just repeat the last two three points? Sorry about that. This
Okay.
one, yeah. Yeah. And
So
the top one. Yeah.
see, this is the sequence length which I've got. I'm
Hmm.
going to Delhi tomorrow. This I've got the embeddings for I, which is of size 32.
Hmm.
This is of size 32. This is of size
Yeah.
32. So this entire, if I take, this becomes 6 into 32 size.
632 is length. Okay.
Yeah,
Got
okay.
it.
Okay. Now when I pass in the batch, okay, for example, I am passing 10 such sentences.
Hmm.
Okay, so then my input becomes 10 into 6 into 32. 10 is my batch size, 6 is my sequence length, and 32 is my embedding dimension.
Okay.
Okay, so they can be passed again in one go. So this embedding and positional encoding and embedding, they take place before the encoder layer.
Hmm.
Okay,
Yeah.
so this is my encoder. So when I give the input here I am doing the positional encoding and the this embedding. Okay, and here I get the output. Now this encoder which is there, it has got two layers. One is the multi-head attention sublayer, MHA, and second is a forward field neural network. Is that clear? Two
Hmm.
sublayers. Okay. Now in the multi-head attention, for example, in the given example in the assignment, they have given sequence length is 8 and embedding dimension is 32 and number of heads they have given 8. Okay, so I'm entering the MHA now. Okay, so I will be covering the MHA. So this is one head, this is another head. So I have got 8 such heads. So in the lecture, what we were told that we will have different weight matrices for everything. Okay, but
Hmm.
inside one head, okay, they will be same. And finally, when we get the output, so I am feeding, you can say 8 into 32. There are 8 heads. So here I should get the in output 8 into 4. And then I concatenate that to make it 8 into 32. Is that okay?
So basically, we divided into four parts.
Yeah.
32 divided into four. Yeah.
Yes. Yes.
Got it.
So this is as per the original paper. But mathematically, we know that if I take a matrix here, for example, three matrices of 32 into 32 size also,
Hmm.
And when then I do so my this WQ, I can take single matrix, sorry, individual matrices for all the heads together. And in that case, size will become 32 into 32. And it will not affect our working of the code because different parts of this weight matrices, they are giving me different semantic relationships. Okay, for example, 32 into 4, first part, okay, will give me here different relations. Here it will be give me different relations. Here it will give me different relations. So it is working similarly as all the splitted heads. Okay, so I can do either I take these so many 8 into 3 24 different weight matrices and then I concatenate, or I take three matrices of 32 into 32, 32 into 32, 32 into 32, and it serves the same purpose. So what happens that I have got now WQ, WK, and WV is 32 into 32. Sorry, this is V. So first I calculate is my attention weights. So attention weights, if you see the original paper, it is softmax of, sorry, before that I have to calculate Q and that. So I calculate Q is equal to H into WQ. H size is what? 8 into 32, and I multiply by 8 into 32. So I get an output of 8 into 32. So Q, K, and V, they are of size 8 into 32. I get attention weights is equal to softmax of Q into KT transpose divided by dimension of K. So dimension of K, you can use either the full root 32 or you use the original. So original K size was what? 8, or it was 32 into 4. So this either you can use 4 or you can use root 32.
Why was it 32 into 4, Vasu? Sorry. No.
32 into 4 because if you are taking the individual case, if you are taking for 8K heads, so 32 is your dimension and K value becomes 32 divided by number of heads.
Okay, just got it.
Okay. So check the size. Okay, what will be the size of attention heads? Okay, Q is 8 into 32, K is 8 into 32, so you get 32 into 8. So this attention weight which is there, it becomes you get 8 into 8. Is that okay? So these are the weights now. It has found the relationships between the words amongst themselves. Okay, so there are 8 words. Now it gets a scores and you have got. And now to get the Z, what you do, or I'm just using something, for example, I call it X. This will become attention weights into V. So this will become 8 into 8. V size is 8 into 32. So I will get 8 into 32. So this is the dimension which I've got from the MHA. One part is remaining. So this entire part which is there, this is the multi-head attention which is taking place. And now we pass through a projection matrix, like in the question they have given again in the assignment, WO. We pass it through a projection matrix like 32 into 32. We can pass it, and when we pass it into 32, from 32 to 32, we get 8 into 32 output, and this is the output from the multi-head attention. So till now we have got what we have got. We have got embedding layer in the starting. Then we had WQ, WK, WV, and WO out, and this gives me the output which is from the MHA. Is that clear?
Got it.
Okay. So now the second part is, now from the MHA we feed it to the feed forward network, FFN. So when we pass, okay, for example, again, if I take the size of batch size 10, I have got an output 8 into 32, which is same as my input size, I pass it through this hidden layer using a ReLU function. So size of this is like 8 into 32. It is the sequence length. So I am passing this 32 one by one. So here in the question they have given 128 is the size of this hidden layer. So size will become 32 into 128, which is W1. I pass it through W2, which will become 128 into 32. And again I get the size of 32. But what is happening in between? I'm applying a ReLU function in between. So this is the functioning of the FFN, that we use the activation function. So again, I get the parameters W1 and W2 here. So till now everything is clear, okay? MHA encoder layer. So this was one encoder layer.
Got it.
Okay. It
Yeah.
is MHA. It has got FFN. So in a transformer, and here we use the embedding layer before the starting. So this was my input. Now output of this, I feed it to the another layer, which is same. Output of this, I feed it to another layer. So this is the layer. I passed embedding. I got the 10 into 32, 8 into 32 I gave. I got output 10 into 8 into 32. I give it to the second layer. Again, I get 10 into 8 into 32. Then again, I get 10 into 8 into 32. Finally, when all the layers outputs are there, so I got this output, final output 10 into 8 into 32. This I pass through the output layer. Now, for example, I had 6 layers. I will pass it through the output layer, which is again a linear layer, projection layer, to get the size. Now, this 8 into 32 is similar, that I am going home and I got different, this 32 with everything. I got 30 these vectors. But I know that my walk-up size was 9. So I have to reduce this 8 into 32 into 8 into 9. So the functioning of this output layer is that only, that you convert this output which is there. Now this will get converted into 10 into 8 into 9. And how the output will look like now? Output will be 8 rows and there will be 9 values here. Now in the inference, what do we do? So here I will get, for example, 0.1, 0.15, 0.2, 0.05, 0.3, 0.7, 3, 4, 5, 6, 7, 8, 9. So I'll get 9 values here. When I use argmax on this, argmax, everything will become 0 and I will get the position where the maximum size is there, 0.8. So I am going home to Delhi tomorrow. If I have got all my process and I have trained well, so this I argmax will come at the same position where the I was there in the walk-up. So if I go back, so I in the walk-up was at 0 position. Okay, so here my final output which is there, which I'm getting here I should have the maximum value, 0.9. If it is happening, then my prediction will match with my token ID. Is that okay?
Got it.
Okay. So now to do this assignment, what do we have to do? We have to define a class multi-head attention. Now multi-head attention, in that what do we have to define? We have to define WQ, WK, WV, and WO. Okay,
Yeah.
we define it and then we define a forward. Okay,
Mhm.
this is I'll get a MHA class. Now from the MHA class, then what do we have to do? We have to define class of FFN, forward network. So in that I have to define W1, I have to define W2, and again I have to define forward. So I will pass it through. So these are the 2 classes. Third class, I will define encoder layer. So in that encoder layer, I will get this both MHA and
Mhm.
FFN to get the, so here also I will define forward. And for all these layers, encoder layer, now final I define an output layer.
Hmm.
Output layer will have a that WL which they have given in the assignment. So again
Hmm.
we define forward. And now with all the components, now I define the entire encoder, sorry, class encoder, which will have all these parts. Okay.
The
I,
sequence of this. Right?
yeah. So I'll just share okay, my this also. Uh, this is I was working on that. Okay. So I'll just show you my this. Is it visible
Mhm.
or shall I increase the size?
It's visible. Yeah.
Okay, so this is directly from the assignment. We have got all the sizes, so they have given the batch size, everything. Then I'll share again this notebook in that group. You can go through
Thank you.
building the sublayers. So this is the class MHSC. So here I
Hmm.
have defined like a D model. D model is the size like a DQ, DK, DV, and I have set a D model percentage heads is equal to 0, and then I have taken the square root of DK. DK is given again, for example, in this case. And then by using the torch manual, they have given clearly that when we are defining WQ, WK, then we have to use these seeds 43, 44, 45,
Hmm.
46. So here I have used NN dot parameter for them, and you can explore what is the difference between NN and parameter and NN linear. So
Yes, I was
for this
coming to
I have
that.
used, yeah, so there is a difference. Okay, I'll tell you, I had asked ChatGPT also, and it had given me a very good answer. So NL linear basically is used to create the fully connected dense layers, such as those are used in the FFN. Okay, so
Hmm.
in the FFN, okay, we generally use NN linear, and when we use in the MHA, we generally use NN parameter when we need to define custom weight matrices, such as those used in the multi-head attention mechanism. So in the
So bas-
MHA, hello,
yeah. So basically, parameters when you want to make it more parameterized, since MHAs are not that linear, right? That's why you use parameter
yes,
rather
yes,
than linear. Linear.
yes,
Got it.
yes. But it is like, so this is the MHA we have defined, okay, these there, and then we define forward. So we are doing the matmul, okay, and then taking the view. So we get the query key and V. Then we use the softmax on the after
Hmm.
matmul, and then we are getting the Z okay, value. So this is the MHA multi-head attention. Then we define the forward feed forward new network. So in this again W1. So these are linear W1
Hmm.
and W2.
Got it.
Okay, and in this feed forward network, we are using ReLU. They have given us that we have to use ReLU. So
Got it.
we are defined and then we have passed through the ReLU. And then finally is the output layer again, which is the linear. It is a projection
Hmm.
matrix. Okay,
Got it.
so and then in the encoder layer, I have got this MHA. So there is another very good concept. If you see the paper, what they do
Hmm.
in the MHA and this is MHA, for example, which is doing. So the input which is coming, they add it and they do the normalization, which is known as the layer normalization,
Hmm.
which happens in the both MHA also and FFN also. The output which is there, they add it, and so this is the normalization which is happening. And here again, this encoder layer, I'm doing this layer norm MHA. So I'm using the torch and then layer norm for both this. So we pass it, we get. And finally, now encompassing all these layers, I have defined the encoder. And
Got
in
it.
the okay, yeah, and encoder, I'm using the embedding. Okay? So first we get the embedding, then we pass through the entire encoder layer. After the encoder layer, whatever I get, then I'll pass it to the output layer. And then I define the model with this, and then training and epochs 30. Then the inference is the same, which I covered just now. That we take the argmax, which is there, and then with the argmax, we check with the token IDs that how many we have got the correct. Okay, so and with the number of layers, when we increase the n layers, just we have to tweak the this encoder code only. So here I make one encoder layer and then I pass it through the number of layers. So with I layer in enumerate self encoder layers, I am passing through the all the layers, and finally once it passes, then I pass through the output layer.
Got
So
it.
this is basically the theory part. In case anybody wants to ask any question, I can repeat again.
No, no, that was
Anybody?
well versed. That was well versed. Me and Pooja loved, to be
Okay.
honest. That was actually well versed. Thanks a lot for that. I was actually getting confused with the entire uh arc. How do you code on a PyTorch?
Yeah.
That
Okay.
was pretty well explained. Thank you for that.
Yeah, yeah. So if you remember this, okay, this again I'll make
Mm-hmm.
it. So this is a single layer. This
Mm-hmm.
is the embedding layer. So embedding layer is before the encoder layer. This is the encoder
Yes.
layer, and in the encoder layer, I've got two sub layers. One is multi-head attention, and again is the FFN. And this is now I keep on passing through these layers. For example, I consider that this is the last layer, and finally I pass to the output layer.
Mm.
So this is the basic, and this is the output. And this output, which is there when I apply, I use the argmax. So argmax gives me, and then I compare it with my token size, which I have passed, okay? And then I can see how many correct okay, predictions I got. So that is the architecture of this.
Got it. Thanks a
Okay.
lot, Lilith.
Yeah. Thanks a lot. Take care. Okay. All the very best.
Yes. Thank
Yeah.
you.
Bye.
Bye.
Bye. Bye.